right, hey guys. So hopefully you kind of had a chance to look at this a little bit. Do you guys want a couple more minutes to look at this problem and we'll go over it, dealing with what we did yesterday? So seeing none, we'll kind of walk through this briefly. Just a heads up, we are doing the integrated rate laws today. So you will need a calculator handy if you have a graphing calculator. If not, I'll show you how you can use Excel or Google Google Sheets. So you can have one of those open as well. And I'll kind of show you how to input the math there if you don't have a graphing calculator handy. That way you can still do the exact same calculations. All right, so for rate laws, remember you kind of have to figure out what order each reactant is. So you have to figure out kind of that ratio of the change in reactant versus the change in rate. So for the ICL, looking at that one, remember you have to look at where ICL is changing, but H2 stays the same. So H2 is constant during these first two trials. So those are the ones that we're going to use for ICL. So looking at the ratio of the concentration is the 0.020 over 0.010 raised to some power is going to be equal to the ratio between the rate. So 5.0 times 10 to the negative third over 2.5 times 10 to the negative third. When we do that, we get 2 to some power is equal to 2. So we know that 2 to the first power is going to be equal to 2. So x is 1, so that means that this is going to be first order whenever we're looking at the ICL. And you have to do that for every reactant that you have. So our other reactant is the H2. So we need to look at where ICL is staying the same, but H2 is changing. So if you look, ICL is the same during the second and third trial. So those are the ones that we're going to use to find the order for H2. So same deal, we do the ratio between the concentration compared to the ratio of the rates. So we have 0.030 divided by 0.010 to some power is equal to the ratio of the rates. So 4.5 times 10 to the negative second over 5.0 times 10 to the negative third. Whenever you do that, 0.03 divided by 0.01 is 3. 4.5 times 10 to the negative second divided by, 5.0 times 10 to the negative third is 9. So 3 to the second power, 3 squared is going to be 9. So that exponent is squared. So this is going to be second order whenever we're looking at the H2. So our kind of base rate law is the rate is equal to K. Remember, there's a constant there. And the ICL is to the first power. The H2, we said, was to the second power. So that's kind of our base rate law. Then it wanted us to figure out the value of the rate constant, the value of K for our reaction. So let me change colors again. So remember, to find the value of K, you're going to take one data set and plug it into your rate law. So I normally use the first one. You could use any of them. I just generally always do the first. So plug that in. So we have a rate of, I'm going to do this right under the table. So 2.5 times 10 to the third is equal to K times 0.01 to the first times 0.01 squared. So we have to isolate K. So we're going to do the 2.5 times 10 to the third divided by 0.01 to the first divided by the 0.01 squared. You can combine that right side before dividing, but you should have gotten 2,500. And remember, a lot of times we do have to put the unit with that. So we had molarity squared, or excuse me, molarity per second divided by molarity cubed whenever you add all those exponents together. So the molarity cancels with one of the molarity cubed. So you end up with the 1 over molarity squared seconds, or it can be written as molarity to the negative second, second to the negative first, to show that it's on the bottom of that fraction. So that was kind of all the stuff we went over yesterday. I'm getting a confused look. Okay. So that's kind of the math that we did yesterday. Looking at another way that these may be asked, I'm going to go up a slide real fast. So it could be something where it gives you the reaction in the rate law and ask you to describe it, ask you what's going to happen. So given the rate law, it wants to know the order with respect to the hydrogen chromate. Well, hydrogen chromate has an exponent of 1, so it's going to be first order with hydrogen chromate. In terms of the hydrogen, it also has an exponent of 1, so it's going to be first order with respect to the hydrogen ion. The hydrogen sulfide has an exponent of 2, so it's second order with respect to the hydrogen sulfide. And then our order overall. So remember, the overall order from the reaction, you add all those superscripts together. So 1 plus 1 plus 2 is equal to 4. So this is fourth order overall. So that's a possibility that it gives you the rate law and asks you to describe it. It can also ask you what happens if you multiply by 2 or multiply by 3 or half the reaction, things like that. So if hydrogen is doubled, so since it's first order, remember we said that the rate and the concentration are directly related. So if you double H, you're doubling the rate. And then it wants to know what if the hydrogen sulfide is doubled. Well, hydrogen sulfide is second order. So this is the one where everything is squared. So if you multiply by 2, it's still 2 to that second power. So this will actually quadruple and multiply by 4 because you're multiplying by 2, but it still has that square on it. So if it was multiplying by 3, it would multiply by 3 squared and multiply by 9. And remember, if it's 0 order, it's not going to change. 0 order doesn't reflect the rate of reaction. Oh, I just saw that there's a question in the chat. Sorry, I didn't have it pulled up. Okay, still some confusion on the units. So on the previous problem, I'm just going to write this over onto the side. But the previous problem, we had the rate, which was molarity per second is equal to K, and then it was molarity to the first and molarity to molarity squared. So that's kind of all of the units. So when we end up dividing, we're doing the molarity per second divided by the molarity cubed. So what happens is whenever you're dividing by molarity cubed, remember if you have this as a fraction, it's the, I don't know what they call it now. We used to do it copy dot flop whenever you were dividing fractions. So if you do the copy dot flop, so you change it to where you're multiplying by the inverse. The molarity cancels with one of these. So you have the 1 over seconds and molarity squared as our unit, which you can leave it like that. But if you don't want to do it as the 1 over, just remember that the exponents can be negative, showing that they're on the bottom of that fraction. So that's where the molarity to -2 second to the -1 comes from. And you could even simply memorize what unit it should be. If it's a first order, well, if you have molarity per second divided by molarity, it's just going to be the 1 over seconds. Yes, the rate is always going to be the molarity per second, so that may help. If it's second order overall, one of the molarities cancels, so it's always going to be 1 over molarity times second. If it's third order overall, it'll be the 1 over molarity squared second. Fourth order overall, like this reaction, would be 1 over molarity cubed second. So the molarity, whatever the overall order is, the molarity in the unit should be -1. So that may kind of help cheat that a little bit. So one thing we're going to look at with integrated rate laws, a lot of times it's going to be graphing the data from rate laws itself. So here you see 3 different lines. There's the purple, the red, and the blue. So let me make sure. The purple line where it goes straight across, if you notice as the concentration increases, nothing happens to that line. So the rate does not change. So if it's a graph that goes straight across, it's a 0 order reaction, because as the concentration changes, the rate does not. The red line is showing a reaction that is first order. So as the concentration increases, the rate is increasing at a constant rate. So they're directly related. And then the blue line is an example of what a second order reaction would look like. As the concentration is going up, the rate is going up exponentially. So it's going to have that curve to it because the concentration is being squared. So that's one thing where if you see a graph like this, know that 0 order is the line that's straight across. First order is going to be that straight slanted line, and second order will kind of have an exponential curve to it. Yeah, Lisa, the x-axis here is molarity. So anytime you see those square brackets, it's indicating a concentration. So it's saying the concentration of A, so molarity of A compared to the rate in molarity per second. It's integrated rate laws. I think I have it linked. I think it says like kinetics to integrated rate laws or something like that. So whenever we're looking at the reactant concentration versus time, which is what that graph just was, we're always looking at the reactant becoming a product, and the general rate is what we did yesterday. Since it's a reactant, remember it's a negative rate because it's decreasing. It's that rate of consummation. Since there's no coefficient, there's no fraction there. It's just like 1/1. And it's looking at the change in concentration over the change in time. So that's that kind of standard rate that we went over yesterday. First thing. So here, if we say the reaction is first order with respect to, anytime you see the WRT, it's with respect to A. Remember, the rate law itself is indicated as rate is equal to K times the concentration of A. So with integrated rate laws, and I might be getting ahead of myself, we can actually set these two factors equal to one another because they're both equal that rate. So whenever we set them equal to each other, we can solve for, we can integrate. We're not actually going to do the calculus to integrate unless you really, really want to. But we can solve and integrate and maneuver it around a little bit to where we get this integrated first order rate law. This is on your reference sheet. So this is not something that you have to memorize. You just have to be able to use it when needed. So on your reference sheet on the first side of formulas that has the AP chemistry equations and constants on it, this is down in that bottom section that says kinetics. So it is written slightly differently. Wait, hang on. There we go. So it is written slightly differently. This is essentially what is on your reference sheet, but it has it where the natural log of A at a certain time, that's what this sub T means, minus the natural log of A at time 0. So initially is equal to negative KT. So either way that you use it, it's going to be the exact same thing. But on your reference sheet, like I said, it has so that's what's written on your reference sheet. So what we can use this for is if we know that rate constant, that K value, and we know how much time has passed and what concentration we started with, we can actually find our concentration at any point in time by using this integrated rate law. And this is the rate law only for first order. There's a separate integrated rate law for 0 order and a separate one for second order. So this is specifically for first order. So first order is looking at the natural log of the concentration. Okay. So we said the first order, the regular differentiated rate law is that rate equals K times the concentration of A, whereas the integrated rate law is the natural log of A, so that equation. There is a difference between these. So the differentiated rate law, what we did yesterday, looks at the relationship between concentration and rate, whereas the integrated rate law looks at the relationship between concentration and time. So they both have concentration, but differential rate law looks at rate, integrated rate law looks at time. So the reason that the integrated rate law is written in this order and not matching what's on your reference sheet is because it's kind of designed to match slope-intercept form. That way it can be graphed. So your natural log of A at whatever time is going to be your y-axis. The rate constant in time is going to be like your slope and your x. And then the natural log of your initial concentration, that A sub O, is going to be your y-intercept. So that's kind of how it's set up to allow you to graph it. So what happens whenever we actually graph this? Like we said, our natural log of A sub O is our y-intercept. Our slope is that negative k. And then t is our x value. The natural log of A sub t is our y value. For reactants, this should be a negative slope because our reactants are decreasing as we're producing products. Whereas if we were just graphing the first order differentiated rate law, just looking at the concentration of with time, it's a curved line. So just looking at concentration compared to time, if this was a straight line, it would be zero order. So since this is not a straight line on the graph on the left that's concentration versus time, we know it's not zero order. So that's where we graph it using the ln to see if it's a straight line, see if it's first order. If it's still not a straight line, then we're going to use the second order integrated rate law, graph it that way to see if it's a straight line. And I'm going to show you kind of these graphs so you can compare them and look at them too. Right, so second order differentiated rate law was like the a squared. For second order integrated rate laws, it's that third equation under kinetics on your reference sheet. It's the 1 over concentration is equal to positive KT plus 1 over initial concentration. And this one is rearranged from what's on your reference sheet. That way it's in that y equals mx plus b. formula so you can graph it. So on your reference sheet under kinetics, it has the formulas in order of 0 order, then first order, then second order. So that kind of makes it easy to remember which is which. And 0 order reactions, like I said, just look at the concentration versus time. So concentration versus time is 0 order. Natural log of concentration versus time is first order. The 1 over concentration versus time is second order. So here's kind of how this can be used. Let me make sure I'm not. Okay. So here we have a reaction, and it gives us time, and it gives us all the concentrations of every substance that we have. And that gives us the basic graph of concentration versus time. And you can see that the NO2 is the blue line. The NO is the red line, and the O2 is the yellow line. None of them are straight when this is a concentration versus time. So since it's not straight, therefore it's not 0 order. So that's one thing that we can tell from this graph. But we don't know if it's going to be first order or second order. So then we have to take this same data and use that first order rate law and then the second order rate law to graph them. So do one with the natural log and one with the 1 over concentration. So here's what those graphs would look like. So remember we said natural log of concentration is first order. The 1 over concentration is going to be second order. And you're looking for what is the straightest. Both of these have a straight trend line on it, but looking at the actual points, which one's the straightest? So if you have that R square value, so you can find this on your graphing calculator. You can input stuff and it'll give you that R square value. Or a lot of times if you're graphing in Excel and stuff, it will also give you that R square value. So which of these two would you say is straighter whenever you're looking at the dots, or the R squared value being closer to 1? Yeah, the one on the right. So this is the straighter line. So therefore, this reaction we know is going to be a second order reaction because the second order rate law is the one that produces the straight line. So that's a way, this is something that is very likely to come up where you have these graphs and wants to know which order is it and why. So you would have to say it's second because the graph of 1 over concentration versus time is straight, meaning it's a second order rate law. So here's another reaction if they did the decomposition of peroxide and they graph the data. What order reaction would you say this is? So if you look, the graph that's straight is the natural log of concentration versus time. So is that 0 order, first order, or second order? First. So this is a first order reaction. So just looking at the graphs, not terrible? Okay. So it's first order because that's the one that is the straight line whenever you're looking at the blue points. So since it's the natural log of concentration, that's the one that produces the straight line. Whenever it's the natural log, that's a first order reaction. So you could even label these, remember, concentration versus time is 0 order. And 1 over concentration versus time is second order. So you're looking at which one produces the straightest line. So always pay attention to whatever the title or that y-axis label is. So here's another way that we'll have to do these. If it doesn't give us the graph and we have to find the graph ourselves. So here's data for the dimerization of butadiene. And it gives us the base reaction. It gives us a series of times and a series of concentrations. It wants to know what's the order of the reaction and then what's the value of the rate constant. So remember that we said K is our rate constant. So the easiest way to do this is to graph it. So this is where we need the calculators, or if you don't have a graphing calculator, you can use Excel, Google Sheets, and I'm kind of going to walk you through this. So what we're going to do is I'm kind of going to walk you through it using both a graphing calculator and Excel at the same time. So I'm kind of going to be going back and forth because it depends on what resource you have. So we are going to actually have to input this data either into our spreadsheet or into a Google Doc or Google Sheets. So real quick for me, I'm going to take a picture of this data because I'm going to have to switch screens. And I'm going to pull this data up. So I'm going to go ahead and open up my Google Sheets. That way you guys at home, whoops. All right, so I'll come back to that in a second. So here's my spreadsheet. And I'm going to put the data it gave me was time. And it gave me the concentration of C4H6. So that's what was given to me. So I'm just going to go ahead and type in what I have here. It was times 0, 1,000, 1,800, 2,800, and 3,600. The other data it gave us were the concentrations. Were 0.01000, 0.00625, 0.00476, 0.0370, and 0.00313. So if you're going to be using Excel or Google Sheets, you can go ahead and set this up exactly like this. If you are using a graphing calculator, you have to go into Stat. All right, so if I turn my camera on, can you guys see me down in the corner at all?
Yes. Yes.
Okay, so if you're on a graphing calculator, hopefully you have some form of TI. Near the directional arrows is this button that says Stat. You're going to click Stat, and it pulls up this screen. You are going to go to edit. So it already says edit, edit, and we're going to click on that. That brings up a blank list. If there's stuff in there, you can delete it and clear it out. But that's where we can start to type this data. So where it says L1, that first list, is where we can put our first column of data. So we can put the 0, the 1,000, 1,800, 2,800, and 3,600. So that's my first column. Then where it says L2, that's where you can put the second column of data. So that was 0.01, 0.00625, 0.00476, 0.0037, and 0.00313. So there I've typed in the exact same thing that's in the Excel sheet, our first column and second column. So you could go ahead and graph this data to see if it's a first order, or excuse me, a zero order rate law. See if this was going to be a straight line. So in the Google Doc, you could highlight these two columns, click the Insert Chart button, and it gives you a little graph. You can always add kind of what it wants. So here we do have a line chart, which is what we want. You could do the individual data points and do a scatter plot. If you click on Customize, you can add features. So you can change what type of chart it is. You can change the title, the color of the series. You can add this trend line. That is that straight line that was shown on a lot of the graphs. You can also click this button that says Show R squared. That's that value that you want to be close to 1 to show that it's a straight line. You can do the exact same thing on your graphing calculator. So to do so, where the Y equals button is, where you would normally graph, up above it is that stat plot. So we're going to hit second stat plot. And it brings up the different plots, the different graphs. So the first one, we want to turn it on. And we want to make sure we put our data in list 1 and list 2. So we want to make sure it's comparing list 1 and list 2. And then we can graph that. Sorry, my calculator's thinking. And mine initially did not show the graph. So if it's not showing the graph whenever you hit graph, you're going to hit zoom in the middle and then go down. It's number 9 is zoom stat. And that will bring up your graph. So as we notice, neither of these are straight lines, whether you did it on Excel or on the calculator. So this is not going to be a zero order rate law. So we have to do one of the other rate laws. Now you could calculate each individual number, plug into the rate law and type in each data point. I'm going to show you how to do it a little bit faster. So that was for zero order rate law. We said that doesn't work. So I'm going to get rid of this chart because that one wasn't it. So remember, second order we said dealt with the natural log of the concentration. So you can actually input the natural log here. Yeah. So on Excel, if you go up to the functions, the thing that looks like the sigma, like the sum, it has like the sum average and everything. But if you go down here to all, and it makes you scroll down, you can find natural log. No, I've never had to do this before because most people are in the classroom and I have calculators. But since you're at home, I had to figure this out. So we have natural log of the concentration. So you can highlight that button and click enter. And what it did, this actually brought up an autofill. So I do want it to autofill, that way it uses the same formula. If it for some reason does not bring up autofill, where the square that's highlighted has this square at the bottom, you can click on that and drag it, and it copies that formula in every other box. So that's going to save you from having to do each individual little click. Now you can do that same thing on the calculator. So we're going to go back to Stat and Edit, and we're going to go over to List 3. And I want you to arrow up to where List 3 is highlighted, like that. So now that List 3 is highlighted, you can type in natural log. So there's a natural log button. So it's next, it's to the left of the 4. So you can do natural log. And we want to do natural log of List 2 because that was our concentration. So you're going to hit second stat, so that pulls up the list, and we can select which list we want it to do the natural log of. So we said we wanted it to do natural log of List 2. So highlight List 2, hit enter, and then I'm going to hit enter again. And whenever I hit enter, it filled in all of the data. So I did not have to go type it in individually for each cell. Now, if we want to see that's our second order reaction, we can graph this to see if it's a second order reaction. So on here, if we want to insert a chart, we want to highlight A, and then if you hold down Control, it will also let you highlight C. So click on A, hold Control, click on C, and now you can insert a chart again. And here it brought up the same scatter plot. We can go to Customize, and it was under Series, I believe, is where we can get our trend line and our R-squared value. So here it's closer to a straight line, but still not entirely a straight line. If we want this on our calculator, so we're going to go back to the second stat plot that we were on earlier. And we want to go back into that first one that is turned on, but where our Y list says L2, we want to change that to L3 since that's where our natural log is. So highlight L2, and you're going to click second stat, so that list will pull up. Highlight L3 and hit enter. Oh, sorry. Addie, was it where I typed in the natural log at on the calculator? Yeah. Okay. So hang on. I'm going to go back to stat where we had our list. So Addie, if you have the L3, whoops. It also helps. If you arrow up and you have L3 highlighted, you can hit natural log, which is down here next to the 4. And then we need to select L2 since that's where all of our data is. So you're going to hit second, and then that stack that pulls up your list. The concentration was in list 2, so we want it to look at list 2. So highlight list 2 and click enter 2 times. And that should have filled in all the data for you. And now I'll go over where you get it to graph again. You're going to go to the second stat plot. So second y equals, where that first plot is on, we click enter. And we go down to the Y list and we want to make sure that it says list 3. So if it doesn't, you hit second stat, so it goes to your list. Highlight list 3, hit enter. And then I can go to graph. And like I said, I graphed and nothing shows up. So if that's the case, click the zoom in the middle and go down to number 9, which was zoom stat. And now, oh, it froze again. And now I have a graph of this. And if you're like, that may be straight, but I'm not entirely sure, I need to know the R² value. So how you find that on the calculator is you are now going to go to stat and then go over to calc. So whenever you go to stat and go over to calc, you're going to go down to linear regression for whatever list we're comparing. So our current graph is comparing list 1, our time, to list 3, which is our natural log. So I'm going to highlight list 2. What? Okay. Oh, yeah, the zoom 9 is how you get it to move. So like I said, in order to figure out the R² value, you go to stat, arrow over to calc, go down to linear regression, which is number 4. We're currently comparing list 1, which is our time, and list 3, which is our natural log of our concentration. So our Y list, we want to make sure is list 3. So we hit second list and go down to list 3 and just hit enter until it pulls up a linear regression. Hang on, my modes is off because it should pull up your R² number. So if yours looks like mine, yeah, hang on, let me get there. If yours looks like mine and you do not have an R² value, it's because one of your modes is off. So if you have an R² value, you're good to go. If it does not, we're going to click on mode and scroll down to where it says stat diagnostics and turn that on. So now if we go through the stat calc and do the linear regression, we get that R² value. So this still isn't that close to 1. It might be our best option, but we can always check to see if that second order rate law is better. So I'm going to get rid of this graph again. And so our second order rate law, remember, is looking at 1 over the concentration. Whoops. So whenever I'm inputting it on the computer, remember, because it's an equation, we do equals, and we can do 1 divided by the concentration, which was in the column B. So hit enter, and that did the value here. And if it brought it up and asked you to autofill, you click yes. If not, where the highlighted square has that square at the bottom, remember you can drag that down to whatever cells you want to copy the equation into. And now we can graph that as well. So remember, if you want to highlight different sections, we highlight A. And since we want it to graph with D, hold down Control when you select D, and it will select both columns. You can insert a chart. And we don't want a column chart. We want a scatter plot. Where'd it go? And with the scatter plot, remember you can customize under series, and you can add the trend line and show the R-squared value. So here it matches up, and it does tell us our R-squared value is 1. So that means that this should be a second order reaction. To do that on your calculator, you're going to go back into Stat, Edit, and if you move over to the right, there is a list 4. So you can do the same thing. Go up to where it highlights list 4, and then you can do the 1 divided by, and remember our concentration is in list 2, so we can do 1 divided by, and we can select list 2 by doing the second stat pulls up the list, select. So if I have the 1 over list 2 where it says list 4 and I click enter, it inputs all of the data for me. So then remember to graph these. You're going to go to second stat plot, and where that first stat plot is on, go and make sure the Y list, since we just put everything into list 4 for second order, change that to list 4. Whenever you graph it, remember if it does not show up when you initially graph it, click zoom 9. So that's that zoom stat, and it pulls it up. It does appear to be a straight line, but remember if you want to double check on your calculator, you're going to go to Stat Calc and go to number 4, the linear regression, and make sure that your Y list matches what list you're on. So we were just comparing it to list 4 for second order rate law. So hit second stat to get that list 4. And whenever we pull it up, it does have our R-squared value as the 0.999, so fairly close to 1. So because the graph of the 1 over concentration is the straight line with the R-squared value closest to 1, this is a second order reaction. So looking at the actual question, so let me pull that back up because we just did a whole lot. You want to know what's the order of the reaction. Well, we decided that the straight line was the one that was 1 over concentration, so it's a second order reaction. It also wants to know the value of the rate constant. So the rate constant, remember, is K. In second order reactions, and I'm going to go back up a second. If you remember, second order reactions have that positive K value as the slope. So that means that the slope is equal to K, which is what we want. If it was 0 order or first order, the slope is equal to negative K. So second order, the slope is equal to K. So we can look at our reaction itself. And yeah, I'm trying to remember how to do equation on here. Oh. Coupons. Sorry guys, my brain just spazzed of how to do this. All right, hang on. I'm going to have to look up how to do it on the computer. Like I said, I just had to learn that. But if you did it on your calculator, your slope, remember, is A whenever it's the y equals mx plus b. So that A value is your slope, which we said was equal to positive k. So that is your k value. So remember, second order, the slope is equal to k. For zero order, first order slope is negative k, so you have to change the sign on it. Let me real quick figure out how to get the equation of the line for those of you using online.
So if the overall, is it overall second order? So that means the unit for
yeah, it's overall second order. Yeah. So that one, you're really only going to have to do these whenever it has like one reactant with this type of reaction. Guys, I didn't look up how to get an equation earlier. I thought it was easier. All right, it says it's under label. I don't know that I saw label. Data labels, maybe? No. All right, let me keep going. Okay, I found it. So under where we click trend line and it popped up this information where it says label, click use equation. And now it brings you up the equation. So here you have your slope is that 0.061. So for you guys at home, because I found that real fast, where we were under customize and we were under series where we had clicked trend line, where it says label under trend line, right above the show R squared, click on use equation, and it pulled up the equation for me. So you can do this either on the computer using Google Sheets or Excel, or using your calculator, whichever way you are more comfortable with, or whatever you have available if you don't have a graphing calculator available. I think I had one more slide. Maybe. No, I had a couple more slides. But this kind of shows you the graphs. So kind of what we went over. So first order reactions. Remember, the straight line is going to be whenever it's that concentration versus time. And the K is equal to the negative slope. So remember, you're going to have to change the sign of the slope to get your K value for zero order. First order will be a straight line whenever it's graphing the natural log of the concentration. And yet again, K is going to be equal to the negative slope. So change the sign of your slope to get K. For second order reactions, the straight line is going to be whenever it's graphing the 1 over concentration versus time, and K is equal to the slope. So the only one that K and slope, you don't have to change the sign, is second order.
Can you change the sign and give us the, and it's supposed to be equation?
Yeah. So like if you had something that was first order and it was negative 2x plus 3, your slope would be negative 2, so your K value would be positive 2.
Oh, so you always want to
Yeah. So just switch the sign on whatever the slope is. Yeah, so that was it for that one. I was going to go talk about Half-Life a little bit because that's first order. Are y'all brain dead and done with me today? Or do y'all want to keep going with Half-Life? All right. So I guess we'll keep going. Half-Life has 7 slides. It does just kind of look over it a little bit. Half-Life is a first order rate law, always. So you guys did this in Chem 1 to an extent. But half-life, remember, is the time required for the concentration of a reactant to fall to 1/2 of its initial value. So if you start with 100 grams, it's how long it takes for half of it to decay. So you would end up with 50 grams. If it goes through a half-life again, the 50 would be cut in half to the 25, and then so on and so forth. And like I said, half-life is always going to be first order for you guys. So here it says you have a first order reaction with a half-life of 100 seconds, and the initial concentration of the reactant was 1 molar. So you started off with 1 molar after 100 seconds. So that 1 half-life, it's cut in half to the 0.5. After another 100 seconds, that 0.5 is cut in half to the 0.25. After another 100 seconds, that 0.25 will be cut in half to the 0.125, and then it will continue going. So even though it's the same span of time, it still cuts in half. So it doesn't cut the exact same amount each time, it just divides by 2. So you do get this kind of exponential graph whenever you're looking at half-life. All right, I'm going to turn my camera off and see if that keeps it to stop lagging. Okay, so like I said, first order reaction is half-life. And they kind of derived that first order integrated rate law with half-life to get this equation at the bottom, which is on your reference sheet. So the half-life, that T half, is equal to 0.693 over K, so over the rate constant. So like I said, you're only going to have to do half-life for first order, and you're using that equation at the bottom, which is on the bottom of your reference sheet. So if you know the half-life, you can find the rate constant. You can find K. If you know K, you can find the half-life and go back and forth. So with half-life, the equation does vary with the reaction order. That's why we said we're only focusing on first order. There are other ones for second order and third order or zero order, but we do not have to worry about those. So I'm actually going to X that out. Oops. My pen went away. It won't let me write on it anymore. All right, so you don't need to worry about that second order. Only worry about that first order that's on your reference sheet. And like I said, nuclear decay half-life is always going to be first order process. So you can use that T to the 1/2 is equal to 0.693 over K. And if you know K and half-life, you can plug that into the integrated rate law to figure out what amount should be left or what initial amount you started with. So here's kind of what an example would look like. So this we did in Chem 1. We set it up a little bit differently. And we were a lot of times given the half-life and things like that. So here we have thallium-208 undergoes beta decay, and it has a half-life of 3.1 minutes. How much time does it take 1 gram of the isotope to decay to 0.175 grams? And then it says given 11 grams of thallium, how much remains after 23 minutes? So here's kind of how we've used it before. Before, you might have taken the 1 gram and kept dividing it in half until you got the 0.175 and figured out how many times you divided in half times the 3.1 minutes.
You're welcome.
If we look at those 3.1 minutes and that is our half-life time, we can go and find K. Now, one thing to note is that K always had seconds as part of its unit whenever we were finding K earlier. So we would need to change that 3.1 minutes into seconds to plug it in. Let me see if I can fight with this and get it to not have that bar at the bottom. Oh, no. There we go. Sorry, it took me a minute to get rid of it. I don't know what made it come up. All right, so like I said, in order to be able to find K, remember K always dealt with seconds, so we need to change the 3.1 minutes into seconds. So we can multiply by 60. So that's a total of 186 seconds. Now, if we know the half-life, we can find K. So you really need K in order to figure out any other half-life problem. So that's where we use that equation we had before of the T to the 1/2 is equal to 0.693. Did I get dyslexic? No, 693 over K. So if we know the half-life, the 186 is equal to 0.693 over K, we can figure out what K is. So remember, since k is on the bottom, you have to multiply it and then divide by the 186. So 0.693 divided by 186 is 0.00372. Now for the unit with this, because it is first order, it's just going to be the 1/2 or the second -1. So since we know K, we can plug that into our integrated rate law that was first order. So first order rate law that was on your reference sheet was the ln of A sub t minus ln of A sub 0 equals negative kt. So we can plug k in with the two values it gave us and solve for t. Is everybody still with me? Okay. So A sub t is going to be your final amount that you have. So natural log of 0.175. Your A sub 0 is your beginning amount. So that's the 1 gram. We said our K was the point, that should be 0.00. That looks like a 6. So negative 0.00372 times t. So to solve for t, solve for time, you can actually type in natural log, and it does open a parentheses for you. So do natural log of 0.175, close parentheses, minus natural log of 1. So this side's total is negative 1.743 is equal to negative 0.00372 times t. So to get t by itself, we're going to divide by the 0.00372, the negative 0.00372. So you should get 468.5 seconds. Now, if this is a multiple choice thing, it may have it in minutes. So remember, to get to minutes instead of seconds, divide by 60. So this is going to be 7.81 minutes. So either of these would be an appropriate answer for how long it takes for that to occur. So now that we have K, we don't have to solve for it again. We can solve this secondary problem as well. But here it says, given 11 grams of thallium, how much remains? So how much is left over after 23 minutes? Remember, you have to change into seconds. So 23 times 60. So this is 1,380 seconds. Since we were given 11 grams, that's our A sub 0, that's our beginning amount. So using that, we can plug into that integrated rate law. So we have natural log of A sub t, which is what we don't know, minus natural log of 11 grams is equal to negative k, so that 0.00372, times our time, which we said was 1380. So I'm going to simplify a little bit. I'm going to do natural log of 11 which is 2.398-ish. And I'm going to do the negative 0.00372 times 1380. So this side is negative 5.1336. So we do have to add the 2.398 to both sides. And we get that the natural log of the concentration of A is equal to negative 2.7356. Now we currently have the natural log of A, but we don't have A. So if you guys remember from math on like the TI-84 calculators and stuff, the opposite is always like the second button. So the opposite of natural log is the kind of e raised to the power button. So if we do e to the power on both sides, that will cancel out natural log, leaving us with A. So if we do the e to the negative 2.7356, we get that A is 0.040649. Sorry, I'm a little dyslexic, y'all. Grams. So that's kind of how this rate law can be used. It's different than what we did in Chem 1, because Chem 1, we were always right on the exact half-life. Whereas here, we may not be exact on the half-life. This may be kind of that in-between time period. And that was it. That was half-life and all of integrated rate laws. I know today was long, but I wanted to get through it. That way you guys have some practice time. Remember, tomorrow we're pretty much just doing review. We might start on Thursday's notes, but not much. But I really want to be able to address questions and do some practice with you guys tomorrow. So that's going to be our goal. Remember, your quiz was moved to Friday. So you really have 2 more days that you can ask me questions. So if you're going through the practice, kind of note or highlight things that you're not sure of or things that I need to go over with you to make you feel more comfortable for this quiz. Any questions for me right now? I know it was a super long day, so I'm going to let you guys go. I will stay logged on if you need me. If you're having individual issues like typing in stuff or graphing stuff, I got you. But make sure that you are kind of looking and practicing some of this stuff, and we'll discuss it further tomorrow. If you don't need me, you guys have a good rest of your afternoon, and I'll see you tomorrow.